As we established in earlier units, our focus and the ultimate destination for the course is to understand the operation of a scramjet engine. Now that you have some knowledge of what a scramjet is, I want to introduce the scramjet design that we're going to use as the basis for introducing the concepts we'll need to analyse hypersonic flows in general and scramjet flows in particular. Here's a sketch of a scramjet-powered vehicle. This is NASA's HyperX or X-43 vehicle that we saw earlier when we were looking at vehicles that have flown at hypersonic speeds. The X-43 is flying from right to left in this picture. The whole underside of the vehicle is the scramjet engine. We'll see that this is a feature of scramjet-powered vehicles, that the engine is very much integrated into the vehicle, so that it's hard to say where the vehicle finishes and the engine starts. Again, we'll look at this in more detail later. Here's a simplified cartoon of a cross-section cut right down the middle of a simple scramjet-powered vehicle. It's not the X-43, but it's a simplified arrangement and one that's amenable for us to analyse. The air comes into the engine from the left. We call this part of the engine the inlet, or sometimes the intake. As we noted when I introduced scramjets, in the inlet the air slows down and its pressure and temperature increase. The arrangement we'll use for the intake is called a mixed external and internal compression system. This arrangement is described in detail in the now classic text on scramjets, Hypersonic Air-Breathing Propulsion, by Heiser and Pratt. It's published by the American Institute of Aeronautics and Astronautics. The flow passes through 3 shock waves in the inlet. Shock wave number 1, 2, and 3. For an ideal flow, this inlet compresses the air so that the flow leaving the inlet is uniform and all travelling in the same direction. It's then ready to enter the next part of the engine, the combustor. In the combustor, fuel is injected and it burns in the hot air that has been compressed by the inlet. We'll analyse the flow in the combustor as one-dimensional flow with the addition of heat, the heat from the combustion of the fuel, and with friction at the walls of the combustor. The products of the combustor then expand through the last section of the engine, the nozzle. It's here that the thrust from the engine is generated. This is a nice, simple model of a scramjet engine, but it has all the components that we need to investigate the fundamentals of hypersonics and of scramjets. The engine layout here is the backbone of the course. This is what I mean. In section 2 of the course, we're going to start by analysing the type of flow that occurs in the nozzle. It may seem strange to start at the exit of the engine, but the regime of flow occurring there is fundamental to all compressible flows. This flow regime is called isentropic flow. In section 3, we'll move on to the inlet. Here, we'll investigate an important flow phenomenon that occurs in compressible flows, the formation of shock waves. We'll concentrate on the types of flows that occur in the combustor in section 4. It will be a simplified model of this flow. We'll not be going into the details of combustion here, but we'll model the effects of combustion by adding heat to the flow. As I mentioned earlier, we'll also include the effects of friction of the flow on the walls of the combustor. We refer to this as skin friction. These 3 sections of the course cover some of the most important fundamentals of flows at high speeds. In section 5 of the course, we'll look at more detail into the additional features that become important when we increase the speed from supersonic to hypersonic. Then in section 6, we'll put all of this together to see how we can model a complete scramjet engine. The final section of the course, section 7, will be the project. And I want to say a little more about the project before we finish this unit. In the project, you'll work your way through the analysis of the inlet, the combustor and the nozzle for a particular engine geometry and a set of flight conditions. By that stage, you'll be able to model the flow and calculate all of the flow conditions at different points through the engine. You'll come up with an overall performance of the engine in terms of the thrust produced. The thrust force T is the propulsive force that the engine produces in taking the air in and pushing it out at increased momentum relative to the engine. In the last subsection, I introduced a performance parameter that's useful for all aircraft and spacecraft engines, the specific impulse, which we denoted as ISP. The specific impulse, you'll recall, is the thrust divided by the weight flow rate of the fuel. We had dmf dt as the weight flow rate. Let's call that m.f. We often use a dot above a symbol to indicate a derivative with respect to time. So m.f is the mass flow rate of the fuel. So that might be in units of kilograms per second. So the weight flow rate is the mass flow rate by the acceleration due to gravity, as we saw in the last section. So we put that together and we get the specific impulse is T over m.f(g). And the units of the specific impulse, as we saw, are seconds. We'll restrict our consideration here to engines operating on a fuel of hydrogen. Hydrogen's the best performing chemical fuel in terms of specific impulse. Let's look at the performance of different types of engines in terms of their specific impulse. We'll plot the specific impulse, here ranging from 0 to 7,000 seconds, as a function of the flight Mach number ranging from 0 to Mach 16. We already saw that rockets have a specific impulse of around 400 seconds when operating on liquid hydrogen and liquid oxygen. Since rockets don't have to take in air to operate, their performance is constant over the whole Mach number range. For the lower Mach numbers, turbojet engines are efficient and able to produce high specific impulses. We don't usually see turbojets flying around and using hydrogen as the fuel, but if they did, the specific impulse would be up in the range of many thousands of seconds. As we discussed in the unit on air-breathing engines, turbojets are not useful beyond about Mach 3 or 4, and ramjets become more viable engines at around about that sort of cut-off range, and can be useful for Mach numbers up to around Mach 5 or 6. Scramjets take over at about that Mach number and, at least in principle, can provide good specific impulse up to high Mach numbers. The limiting Mach number for scramjets, as we saw, is still to be found. We see that the specific impulse of air-breathing engines is potentially superior to that of rockets for a wide range of flight Mach numbers. This plot is the classical one that shows why we might be interested in using scramjets to power the stage of a launch vehicle. We might choose to replace a rocket stage with a higher specific impulse scramjet stage. So if we could replace a rocket stage with a higher specific impulse scramjet stage for a launch vehicle, we might be able to get a launch vehicle with a better overall performance and more payload into orbit for the same takeoff mass. In the project for our scramjets, we'll be looking to see if we can reproduce a curve of this form by collating the results from the analyses of all the students in the class for their individual scramjet conditions. This brings us to the end of this section. If you're looking to take the course for credit, make sure you complete the quiz.